So, friends, let us continue with the discussion on planar truss system, which we had in the last lecture. We are talking about the computer method of structural analysis applied to planar truss system examples. We had this problem in the last lecture that there are 5 member truss as shown in the example here. We arrived at the unrestrained and restrained degrees of freedom. Then we made this table and calculated the transformation coefficients C x and C y. Then we estimated the stiffness matrices and transformation coefficients matrices for all the members and worked out the global stiffness matrix of each member as A B, B C and so on. Okay. So, we got A B, B C, C D, B D and A C all the members. Let us continue with the discussion on estimating the joint loads for this problem. So, looking at this example, the joint forces are applied at degrees of freedom. You can see here delta 1, the forces are applied at 40 and 20 here. Let us do that at this is 40 kilonewton and this is 20 kilonewton. So, now the joint load vector at delta 1 you get 40, okay, and delta 2 0, delta 3 0, delta 4 is again 20. So, let us do the joint load vector in a simple term like this. So, the joint load vector bar, that is the global, is plus 40, 0 0, minus 20. The labels could be 1, 2, 3, 4 and 5, 6, 7, 8. So, there is a partition here. Okay. Now, I can apply this equation delta bar, that is a reference axis displacement, will be given by k u inverse multiplied by j l u. Now, I have k u inverse after assembling the stiffness matrix. We get k u inverse as, let us first find k u, which will be actually E times of 0.0015 minus 0.0005 minus 0.0010 and 0, 0.0018, 0, 0, 0.0015 and 0.0005 and 0018 with symmetry here, and the labels could be 1, 2, 3 and 4 for the unrestrained degrees of freedom. Now, I find k u inverse, which will be 1 by E 10 power 3, 1.5534, 0.4628, 1.1319 minus 0.3372, 0.6995, 0.3372 minus 0.1005, 1.5534 minus 0.4628 and 0.6995. Now, the labels could be again 1, 2, 3 and 4. This is k u inverse. Now, apply this equation to find the displacement in reference axis system as k bar u inverse multiplied by j l u bar. I substitute this, now I will get delta bar with reference to the reference axis system as 1 into 10 power 4 by E 6.8881, 2.0521, 5.4532 and minus 2.7479. Okay. The degrees of freedom are going to be 1, 2 and 3 and 4. So, that is my global displacement vector in the reference axis system. Once I get this, I can always find the member forces in each member. So, for AB, let us say I want to find the member forces for AB, which will be V bar 6, V bar 2, H bar 5 and H bar 1, which will amount to minus 25.6509 plus 25.6509 and zeros. Similarly, MBC, these are all M bars, will be V bar 2, V bar 4, H bar 1 and H bar 5, which will be 0, 0, 14.3491 and minus 14.3491. Let us do it for MCD, which will be labeled as V bar 8, V bar 4, H bar 7 and H bar 3, which will be 34.3491 minus 34.3491 00. Similarly, M bar BD, which will be labeled as V bar 2, V bar 8, H bar 1 and H bar 7, which will be minus 25.6509, 25.6509, 25.6509, again 25.6509. Let us work out. M bar AC, which will have labels as V bar 6, V bar 4, H bar 5 and H bar 3, which will amount to minus 14.3491, 14.3491, minus 14.3491 and 14.3491. Assembling all these M bar values of all the members, we can always find the end reaction as I show you here now. So, this is my given truss system. With these are my supports. Okay. Now, if you look at the final reactions are going to be plus 40, then this is minus 20, then this is minus 40, then this is plus 60, this is 14.349 and 25.651. Checking that, if you take moment about the point A, okay, so it is going to be 40 into 4 plus 20 into 4 again minus 60 into 4, which will be 0, which is confirmed. Okay. So, that is how we get the final reaction. One can also find the forces in the members, as we can take it from each member. So, member 1, member 2, member 3, member 4 and member 5. Let us do it separately for each member. So, this is 25.65 and 25.65. You can always find this from this vector. If you say MAB, it is V6. If you look at the degrees of freedom, you can always mark the degrees of freedom. So, this is going to be 1, 2, 3, 4, 5, 6. So, the labels are 6, 2 and then 5 and 1. Okay. So, confirming that, look at AB 6, 2, 5 and 1. So, 6 minus 2 is plus. So, I am marking it as minus and plus. Okay. Other is 0. Similarly, for this member, this is going to be 14.349 and 14.349, and for this member it is 34.349 and 34.349, and for this member it is 25.261, 25.261, similarly 25.261 and 25.261, and for this member it is 14.349 and 14.349. This is also 14.349 and this is 14.349 positive. So, I got the reactions now. I convert that into the system. Okay. So, I get now the values as minus 40 plus 60 and 14.349 and 25.261, which is as same as what you get here. Okay. So, the problem is now solved. We will do one more example. Now, in this case, first we will discuss the computer program for this problem. You know, there are 5 members in this problem. So, there are 5 members. We entered the length of the each member, we entered area of cross section of each member, then we entered the values of theta. Please understand, if a member is arbitrarily oriented, this is my xm and this is my ym. If this is my reference axis, theta is always measured anti-clockwise positive. Enter the values of theta, then labels of every member is entered, which we already have with us. For example, L1 member 1 has 6251, see here member 1 has 6251. Okay. So, similarly we can enter these members labels, then we find the transformation matrix for each member, then we obtain the assembly of the local stiffness matrix of each member and find the global stiffness matrix of each member k bar, then we assemble them and get the stiffness matrix completely, partition them and get the unrestrained stiffness matrix and get the inverse of the stiffness matrix, enter the joint load vector. The joint load vector, you can say from here I write down is going to be 40 0 0 minus 20 0 0 0 0, that is the value I have. Let us compare this with the joint load vector here, which is exactly the same. You can see 40 0 0, okay, and minus 20 4 zeros. So, this is exactly the same here you have, is it not? 40 0 0 minus 24 zeros. Okay. So, we have the joint load vector, then we found out the unrestrained displacement values, then we find the member forces, then we check the member forces only for each member. Okay. This is the computer program we have, which we have used to solve this problem for simple planar truss with 5 member. Let us do one more problem. This is a typical output, which we have the answers for this member. I wish you should go through them thoroughly and try to compare the values what we have obtained for this member. Okay.